Okay, as mentioned earlier, aim is to find associations among disease using multiple data sources. Authors in this paper talk about a pipeline consisting of discrete automated stages where each next stage is dependent on the previous stage. Major stages in this pipeline are data preparation. So you essentially identify disease of interest for test and control groups. You find patients with those disease of interest and you load their ICD-9 code history. Second step is to identify associations. So they run ADAMS to establish statistically significant associations and to also search for associations in other data sources. And finally, there is a step of analysis where they draw a network diagram combining ICD-9 codes with data from different data sources. Once we have data prepared for both test and control cohorts, next stage is to identify associations. They use ICD-9 data to get candidate associations first. So, idea is to calculate p-value for each ICD-9 code in test versus control. This is like univariate analysis where hypothesis of association is tested individually for each ICD-9 code. Note that because of asymmetric hypergeometric function, they can only identify positive associations. Since we are testing multiple hypotheses, one correspond to each ICD-9 code, it's important to correct for multiple hypothesis testing. And they do this by false discovery rate using bootstrap method. So bootstrapping, I would like to emphasize on this method, which is used by the authors to compute false discovery rate. In bootstrapping, idea is to create randomized guess and controlled sets based on observed test and control cohorts. Essentially, erase the test and control labels and reassign them at random and do the test again. Repeat this k times and check how many times association is found in randomized guess and control set. This fraction gives the false discovery rate. Bootstrapping, we are able to essentially build empirically a null distribution, and hence it's a quite popular technique which is used to get statistic results but hasn't been extensively used in BMI folks. And the final step is to combine data from multiple data sources and do this by network diagrams. So they create a graph of node D and its correlated disease found using the previous step. Next step is to find correlated disease of D in other data sources like PubMed, Wikipedia. The new associations found using other data sources are fuzzily matched with the existing nodes in the graph. In case matching is found, then new nodes and edges are added. Note that fuzzy matching is based on UMLS terms and Levenstein distance. They also do post processing because the graph constructed in the previous step can become quite large. They have a concept of supernodes to do grouping of similar nodes together. There is a control available to also remove edges between supernodes to avoid any false association. This final graph can be used to interpret associations and data source from which it comes.